All right, good afternoon, everyone. So last session, we discussed essentially graph neural networks. We started our discussion. The vast majority of what we discussed before was just basically building up toward graph neural networks. So today in this session, we're gonna look at some changes that we can make to the base, essentially graph neural network in order to improve its performance. So last session, we looked at a general basic propagation rule for graph neural networks. In this basically propagation rule, we were computing the node embedding. So the idea was that as the input to our graph neural network, we had a graph and the features represented on basically different nodes in this graph. Then we wanted to use a concept called neural message passing in order to propagate this these features over the graph. We wanted to propagate it forward to get some final node embeddings, and then we can use those node embeddings for performing different tasks on graphs. So just to reiterate, let's say that we have this graph, we have this node. Just to reiterate, let's say that we have this graph, we're trying to look at this node and how messages are basically propagated to that node. In order to show one iteration of our neural message passing, we were trying to construct a subtree pattern rooted at the given node with the height as the number of iterations of our graph neural network. So let's say that if I have a single iteration of neural message passing, my information are at node 1 are the messages coming from its neighbors, and I can represent that using this subtree pattern with height 1, right? So now we want to look at basically different elements that come together to construct a graph neural network. Let's say that, let's basically take the subtree pattern that we have here. And the first element that we need to build our model is an aggregation function. This aggregation function essentially defines how, in what basically order, or basically with what principle we are gathering information from different neighbors that we have, right? So so here 1 is getting information from 2, 3, and 6, and these basically paths are showing how information are coming, and the function basically aggregates those. Now, a second principle that we need to have is principle of update, meaning that now that we have the message from our own neighboring nodes, we also had basically nodes its own previous embedding in the previous iteration. Now we want to combine these two. Potentially combine these two. We can do, for instance, disregard the previous state of the node itself. So given those elements, we want to define an update function. So that basically takes whatever that aggregate function generated and turns that into a new embedding for the node that we are discussing. So combination of these two gives us our graph neural network layer, a single layer of basically our propagation layer. Now that I want to generate a graph neural network, I might want to stack many of these on top of each other. And I might want to stack many of these on top of each other. And that would be essentially we can represent that using another neural message passing layer that gathers information at a basically higher depth. So here, for instance, we can see that in first layer, we have gathered information from these series of nodes into some basically incident node. And then in the next iteration, we have those information from the previous layer and propagated to basically node 1 that have edges incident from 2, 3, and 6. So now let's say that we have all the layers that we want, and then we need to define some objective function on top of this problem. Now we discussed that in graphs we have multiple, unlike many machine learning tasks, we don't only have representations that basically feature vectors that represent the whole graph. We can also have feature representations, feature vectors that represent each nodes, right? So that's basically basic idea. And we have tasks corresponding to those. So based off of the type of task we had, if it's an edge level, node level, graph level, subgraph level, or basically whatever that the task is, we have essentially different objective functions. Now, the majority of the discussion that we will have today is on how to improve the main principles of within each neural network layer, meaning aggregation and update, in order to improve the essentially model that we're dealing with. And in general, what options we will basically normally have in order to basically from which we can pick our aggregator or our update functions. And we will slightly look at how we stack these layers together and what will basically happen if we stack too many layers on top of each other. So the first concept that I want to discuss is neighborhood normalization. So I want to first start with basically variations that I can apply to the aggregation step, right? So in many graphs, we have basically nodes that vary in the degree. So let's say that we have a some social network, right? Social network, and then different nodes have different degrees over this node. And the embeddings, if now we sum essentially the embeddings, for instance, of the nodes for different nodes, we will get values, we will get magnitudes that are basically very different from each other, right? So let's say that I'm comparing the messages gathered, aggregated for two different nodes. I'm denoting with VI and VJ. Now, let's say that VI has too many neighbors, so the magnitude of the embedding, the message that I've gathered from the neighbors is way higher than that of node J. So this will cause an imbalance within the graph during the training, and we need to sometimes we need to find a way to deal with this imbalance. This imbalance will cause for instabilities during our training. So one might think that the one straightforward approach to address this can be normalizing. So let's say that I have basically a series of nodes, Vj, that are neighbors of my node Vi. And then each of these nodes, Vj, has its own embedding. I'm showing that with Hj. And then in the aggregation step, what I'm doing, let's say that I'm using a sum, as we have done so far, as my aggregator. And then I'm summing over all these embeddings, and I'm dividing that by the degree of that node that we have. So I'm normalizing that using the number of nodes that are connected. So this brings some balance to our problem. So this is one way to normalize it. Another approach to normalize this problem is by using this relation, where this time I'm not normalizing it only with the basically over the degree of the node, the receiving node. I'm normalizing each embedding by the square root of the degrees of the two nodes at the two ends of the edge, right? So each embedding that is coming from, let's say, node J is normalized by square root of degree of the node that basically is sending me the embedding and degree of the node, the VI, that is receiving the embedding, right? So this is called, basically, this is another method to normalize the messages, and it's called a symmetric normalization. Now, the essentially aggregators are multi-set functions, meaning that we have labels on the basically neighboring nodes. They are basically embeddings, essentially. We can just simply think about them as labels, right? Let's say that they're one-dimensional. And then when we aggregate this, there is no restriction on if these nodes are basically equal to each other or not, right? So two different nodes, for instance, 2 and 6 can have the same embedding, right? So when I gather this, I want to construct a basically the set of all the different embeddings. I will have a multi-set, meaning that it is a set, but it also has basically a variable corresponding to the number of repetitions of different labels, right? So it means that I can have more of one than each label. So now we can do some improvements on these functions. So let's say that I'm still using a sum, and I'm summing over all the essentially embeddings that I have. I can apply on each of these embeddings a neural network, a just fully connected neural network that extracts feature from the embeddings before I propagate it to a neural passage, basically a neural message passing layer. So then I will have my formulation as the sum over f theta of hg, where hg is just the embedding corresponding to neighboring nodes, and f theta is now a neural network, which is parameterized with some parameter theta. Now, if I want to show that in this figure, I will have first my embeddings pass through this f theta. Then I basically kind of extracted new features from these embeddings, but I'm just looking at them as different basically data points. I'm not combining anything with each other. And then I generate these basically new embeddings. I'm showing them with green. This can be potentially with different dimensions than these basically input ones. And now I can just sum over the new embeddings basically to construct our message. So I can take this idea further, and let's say that now so I constructed this message by gathering all the embeddings from my neighbors. I can also improve that by applying another layer of neural network, just a fully connected neural network on top of my output. And that will basically take something out of this output at 1, basically aggregated message as 1 at 1. So then I can represent my message from basically the message from neighborhood of node I to I as f phi of sum over all neighbors of node basically v. Then f theta of hg means that my basically embeddings hg goes through first a multi-layer perceptron. Then I get basically some new features here. I sum over them, and then I get this guy, and I pass it through some basically function. Now I have two layers of basically two fully connected neural networks. One is f theta, one is fp, which phi and theta are simply showing the parameters corresponding to different models that I have. Now, if I want to show that on this figure, essentially, I gathered this new information on 1, then I passed them through some function fb, and then I got essentially my new embeddings, my modified embeddings at node 1, my basically modified message at node 1.
Did I share with all the nodes, or you just share?
Yeah, so in this model that you're showing, it is, but I mean, technically speaking, you can condition it on some property of the node as well. But then, if you have some graph that has too many nodes, you will have new parameters for every one of them. It's going to be maybe over parameterized. So the model that we're discussing is just constructing every layer, similar to what we discussed last time, that we can also have layers that from one node to the other node, it has a different basically set of parameters. But yeah, so this is a similar thing. We are just taking that graph layer and we are applying it on different nodes. We want to keep for now, we want to keep the structure the same. So then we all right, so far we have looked at only one function that can be used to aggregate basically information from the neighbors in order to be able to construct a message, right? Now, but there is more than that. The only thing that we have discussed so far is summation, meaning that we have basically different embeddings from different nodes. At each iteration k, we're just summing over the neighbors for node n, and that's gonna be our aggregator. Another function that we can use for this is element-wise maximization. So this time we are just basically gathering the multi-set of all the embeddings that we have in our graph, in our neighborhood, and then we basically stack them together. We just do an element-wise maximization through some dimension that we have stacked them basically in that direction, and we basically construct our new message here. We call it M. So likewise, another method to do that is just using minimization, meaning that similar to methods before, we're just stacking everything together at each basically neighborhood, and we're finding minimum elements through different neighbor nodes, and that's gonna, at the end of the day, construct our message. So these are three different aggregation models that are being used. There's also mean, which is essentially similar to the summation, right? Now, so far, the models that we have discussed were permutation invariants, meaning that if you have basically a set of nodes, and then this set of nodes have embeddings, you get basically, if you sum over all these embeddings, it doesn't matter how you basically, what's the sequence of the embeddings within your multi-set of neighbor basically embeddings, right? So if node one is come first or second, still their sum is the same. Their maximization of element-wise maximization is the same. Their element-wise minimization is the same. But some approach is to just not use that. Instead, we use a function that is permutation sensitive, right? So now the question is, my function is basically permutation sensitive. How should I get some message that is permutation invariant or approximating a permutation invariant problem? The answer to that is by going over different permutations that we can have, right? So we have a function that potentially takes a sequence of basically different nodes and compute some message. And then for basically, like last time, we looked at a model that had multiple permutation for 4 nodes. We take the neighborhood, we go over different possible permutations that we can have within that neighborhood, we sum over that, and that's gonna, at the end of the day, give us a permutation invariant, right? So let's look at mathematics behind that. Let's say that we have permutation P, and we construct a set of all possible permutations using basically pi, right? So now we say that this is all a set of all possible permutations for our neighboring nodes of a given node Vi, right? So VJs can have different basically order, and that's the set of those orders. So now let's define our function f theta to be a permutation sensitive function. Now I'm giving a sequence of embeddings from my neighborhood. Now see, this is the total number of the embeddings that I'm passing to this function of theta is the size of the neighborhood of node vi. So I'm just counting embeddings for different neighbors of node vi. And then I pass them in a sequence to a function f theta. And then this basically index p is just showing the corresponding order of these nodes, right? So corresponding permutation of basically these nodes. So I'm writing it 1, 2, 3, but next time it is changing based off of this permutation p, the order of these embeddings. And then this function f theta returns some message, and then we go over all possible permutations p that we can have. So I basically try different orders of these embeddings, I pass them to a theta, and then I sum over all of those, and essentially I basically divide them by the total number of different permutations that I have. Then that will give me a message that I can basically use. Now, you might think that now there can be, for instance, millions of permutations for a given neighborhood. You need to sum over millions of permutations only to get the message for a single node, right? So in order to remedy that, we need to have some method to approximate this message, right? So we need to approximate the summation here. So the way to do that is to, let's say that we have this function, we want to approximate this only with a few permutations. So what we do is that we sample some basically permutations from this function, and then we only average over a basically randomly sampled number of permutations from this neighborhood. Let's say that I have T sample, basically I take T samples P from this set of permutations, and then I'm just computing F theta with those subset of all possible permutations. And that will basically usually give a good approximation of the message that we want to compute.